Okay, so we are looking today at 4.3b. And this one is super short and it has no questions attached to it. Okay, 4.3b. So, dissociations of, are we good? Okay. Dissociations of diprotic and triprotic acids. This is 4.3a, which you should just have picked up from the side counter just now. So when you have a diprotic or a triprotic acid, I mean, honestly, all you need for this entire thing is just to read this first box. Only the first dissociation is important in Ka calculations. Okay? Diprotic acids actually undergo 2 dissociations, but only the first one produces significant quantities of hydrogen. The second dissociation produces some hydrogen, but only a teeny tiny itty bitty amount, and so you can just ignore it. Okay? So if we had a question like, what is the concentration of hydrogen in a 0.2 molar solution of carbonic acid? First thing you have to ask yourself, is this acid strong or is it weak? H2CO3. Grab yourself your data booklet and look that up. Is H2CO3 strong or is it weak? It is weak. And if it is weak, what tools are we going to use? We're going to use a rice table. Did I come up with my stupid? Yes, I did. Yes, it was block 3 that hasn't heard about it yet because they were on Wednesday. Okay, so we're going to use a rice table and we're going to use Ka. We're not going to go through the whole problem, although it's all here if you want it. But basically, the question is then, we need to do a rice table. Which of these 2 equations are we going to use? Are we going to take off 1 hydrogen or are we going to take off both hydrogens? And that's what will cause students, questions sometimes, right? They'll.
Good morning, everyone. Today, Student Council is holding Winter Wonderland, an annual event where students can earn many prizes. This year, we have a bunch of prizes, including board games, a Nintendo Switch, AirPods, and a voucher. Could I please have the following t-shirts have the students come down to the lower pond? Ms. Riley, Ms. Bell, Mr. Asper, Ms. Barski, and Mr. Blazer. Thank you.
Okay. Only the first dissociation is important, which means that you only take off how many hydrogens? 1. Okay, so just 1 hydrogen. Now, how do these actually take place? Well, in reality, there is dissociation number 1 where one of the hydrogens comes off. So that's dissociation number 1. And you'll notice it has a Ka with a value of 10 to the minus 7. Yes? The second dissociation, where the second hydrogen comes off and you're left with CO3 2 minus, its Ka value is much smaller. It is 10,000 times smaller, yes? Power of 10 to the 4 times smaller. So the amount of hydrogen produced by the second dissociation is so small that we just ignore it. And you know why you're going to be very glad of that? Because if you actually had to do the calculation, what it would look like is you would have your normal race table, okay, where you have your initial concentration, 0.2 molar. Remember, what are the original concentrations of the dissociated ions always? The initial ones? They're always 0. And then we would have plus x, minus x, blah, blah, blah. Plug everything in, get your Ka from the data table, assume x is insignificant, yada, 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 solve for x, and we get hydrogen ion concentration. That's super nice, yes? Just a flash review of yesterday. What if we had to do the second dissociation? Well, now in our solution, we have hydrogen, which is equal to this, but also this is our concentration of the HCO3 as well. Why am I scribbling that? I thought it was a highlighter. Okay, so both hydrogen and HCO3 are 8.6 times 10 to the minus 8. So if we were to make a new table, we would have 8.6 times 10 to the minus 8 here and here. And now we would have to add x. And now we get, oh my God, we get a quadratic and there's nothing we can do about it. So we would have to solve a quadratic. Just believe me, I did it this morning just so you guys could feel good about it. Here's our quadratic, yuck. Okay, and I cheated and I went online to a quadratic equation solver so that I didn't have to, x equals minus b plus or minus root of b squared minus 4ac all over 2a. Anyway, I didn't have to do all of that. I just plugged it all in and I got 5.59 times 10 to the minus 11. So my new amount of hydrogen, the extra hydrogen I got, would be 5.59 times 10 to the minus 11. And so I now would have, this is from the first dissociation. This is from the second dissociation. There's my total when I add the two up. But you'll notice when I round to sig figs, does this number look familiar? 8.6 times 10 to the minus 8 is how much we got from the first dissociation. So I would have done all that hideous, horrible work for absolutely no reason, okay? So when you have a diprotic or a triprotic acid, only take off one hydrogen and leave the rest alone. That will be different than what we do in titrations, but we're going to leave it there. So that's 4.3b. 4.3c. And then I'm going to leave 4.3d for you to learn on your own at home from Mr. Colger. And I will also be making a video as well. Okay, so there's going to be a video for that one. Weak acids, finding the Ka from the data. So you will be given the concentration of the acid initially, and you will also be given the concentration of hydrogen, or the pH. And from those, you can find the value of the Ka. And I decided, since we had just looked at diprotic acids, that in our example, we would have an unknown diprotic weak acid. Yes? It is found to have a hydrogen ion concentration of 0.0060 molar when we mix a 2 molar solution of the acid. Things you need to realize about this question: if they give you a hydrogen ion or a pH, that is always the equilibrium concentration of hydrogen or pH that's given in the question. The acid, do you remember the concentration of the acid is always the original concentration, yes? Now, because it is a diprotic acid, we have to have an H2, and I've just called it A for acid, yes? You could call it HW for weak, you could call it HX for unknown, you know what I mean? Like, it doesn't matter what you call it, just don't call it, you know, HC, because that would be like carbon, you know, try not to give it an actual element that would be something, okay? And remember that it is only the first dissociation of a polyprotic acid that is important, so we only take off one hydrogen. You could do this with monoprotic, but I thought it would be nice to have an example with a diprotic since we just looked at that, okay? Oh, look, I've written it again. The concentration of the acid in the question is always the initial concentration. The H plus or pH is always the equilibrium. So when we first place, oh, this should say H2A. I changed the question this morning. None of the acid is dissociated. So the concentration of H2A, let's go back to our question. What is the concentration of H2A? 2.50 molar. And what is the concentration of the H and the HA? Oh, this here should say HA minus, not W minus. What can we say about the initial concentrations of H plus and HA minus? They are 0, okay? So we'll plug those in, and we're going to use rice. And we know also, we are told that the equilibrium concentration of hydrogen is, where did it go? The equilibrium concentration of hydrogen is 0.0060 molar. Hi, thank you. So if we know this value, we can solve for the change, because to get from 0, it's not grade 12, so I'm just going to talk over them. In order to get from 0 to 0.06, you obviously have to add 0.06. Yes? Okay, so we can solve for that. And now, because everything is 1 to 1 to 1, we can fill in all the changes as being 0.060. Yes? So if you know the initial and you know the equilibrium, you can find the change. Yes? Oh, well, that's interesting. Okay, let's just go with 0.060, because I think I did the answer key for that. So 0.060, let's get rid of that. There we go. And so now we have 0.060 squared. Oh, hang on. Because this is minus 0.60, we can actually do that subtraction, and we get 2.44. Yes? Sometimes people will do something silly. They will say, assume 0.060 is insignificant. Is that true? No. In fact, the only time you make an assumption is if your change is X, if your change is actually an unknown. I do know that some people will sometimes put X's in here and then plug in numbers later, but that does lead to them sometimes then saying, oh, let's assume that X is insignificant, when actually it's a real number and it's not actually insignificant. So if you have a real number, please, please, please put the real number in the race table, okay? Oh, and then once you've done that, you just plug it into KA, and it's usually some really simple math, right? We've got 0.060 divided by 2.44, and that gives us a KA here. If we had made that assumption and assumed X was insignificant, we still would have had 0.060 squared, but we would have been dividing by 2.5 if we didn't subtract 0.6. And that would have given us a Ka of 1.4 times 10 to the minus 3, which is wrong. Okay? One last example, and then it's quiz time. Or do you feel like you got it? You got it? Okay. If anyone would like the second example, I can pop it up on Teams. You can say, hey, Ms. Spence, please give us the second example for 4.3C on Teams. The other thing is Colger has videos on these topics as well, so you could always look up him also.